Hi, I'm Maria. I've been in data and AI for almost 12 years, focusing most of my career on the MLOps.
And I'm Başak. I've been working as machine learning engineer for the past 8 years with a relevant educational background in computer science and AI.
We are both huge fans of Marvel and the MLOps, and that's why we founded Marvelous MLOps.
It's our space to share practical insights through blogs, videos, and hands-on content to bring your ML pipelines into production.
This free course is your complete guide to end-to-end MLOps from Databricks.
With Databricks recently announcing Free Edition, we saw the perfect opportunity to help more people to build real MLOps applications.
Let's dive in and get your production ready. 3 hours of content is waiting for you. In Lecture 1, we will talk about MLOps principles and tooling. Then, we'll set up a Databricks Free Edition and show how you can utilize Databricks developer tools. In Lecture 3, we will get started with MLflow and deep dive into MLflow experiment tracking. After that, we will log and register a model. In Lecture 5, we will discuss different model serving architectures and when you should use them. In Lecture 6, we will deploy a model we registered earlier behind the model serving endpoint. We'll also discuss how A/B testing differs from traditional traffic split. In Lecture 7, we will go into Databricks asset bundles and we'll deploy the whole machine learning pipeline. Then we will talk about CI/CD pipelines and deployment strategies. To finish up the circle, we will talk about monitoring in Lecture 9 and we'll deploy a lakehouse monitoring on practice in Lecture 10. Welcome to the first lecture of our MLOps with Databricks course. This is lecture 1 out of 10, and I will be talking about MLOps, how MLOps differs from DevOps and why you should care about it. You probably have seen this definition before. MLOps is a paradigm that aims to deploy and maintain machine learning models in production reliably and efficiently. But what does production mean? Production simply means that the output of machine learning model is used by the user and delivers value. And it can be anything. Let me give you an example. So let's say we have a manager of fulfillment and he gives a task to a data scientist to develop a demand forecasting model. So data scientist works on it, has a POC, probably a Databricks notebook, probably a big one, maybe 1,000 lines of code. And well, we want to deliver this value consistently, so he decides to schedule it in Databricks, just because you can and it makes your life easier. This notebook typically consists of 3 steps roughly. There is some data processing, there is model training, and there is computation of predictions, and those predictions are then written to a delta table, and the fulfillment team can pick it up and use it in their business processes. Is it production? Technically, yes, because it delivers value and is used by the end user. Is it efficient? Maybe. It's better than running code by hand every week. Is it reliable? No, it's not. It doesn't follow the MLOps principles. Let's dive into those. The main principle in MLOps is traceability and reproducibility of your machine learning model deployments, which means that for any machine learning model run or deployment, you should be able to look up unambiguously the corresponding code, commit on Git, infrastructure, environment used for training and serving, data used for model training, and also generated machine learning model artifacts. You should be able to come up with any combination of these different things and reproduce it later. So this is just one group of MLOps principles, but there are many more. And in this course, we are mainly focusing on these 3 types of principles. So traceability, reproducibility, code quality, and monitoring. How do you ensure that all these practices are being followed in your projects? You can argue that documentation principles can also be considered as MLOps principles, that you should be able to look up why certain decisions were made, why certain architectures were used, and it is especially important if some team members leave the team. A/B testing, experimentation can be considered as MLOps principles. The same goes for explainability and feature stores. Those are definitely important. if you are evaluating MLOps maturity of your project. Even though in MLOps principles come first, you cannot follow principles without tooling. Let's talk about the tooling. The first tool in MLOps is version control. Your code must be versioned, and there are many tools for that. GitHub, GitLab, Bitbucket. Whatever you have in your organization, just use it. You also need CI/CD pipelines. You can use Jenkins, Azure DevOps, GitHub Actions, GitLab CI/CD, anything you have at your disposal. You need an orchestrator. You can use Apache Airflow. You can use Argo workflows, Databricks workflows, and maybe more specific orchestrators for ML, such as MLflow. You need model registry. MLflow is probably the most popular one. You need a compute to train your model. It can be some Databricks compute or Kubernetes, or you could use Azure ML or SageMaker. You need infrastructure for serving. It can be also Kubernetes. You can deploy models using Databricks. You can deploy endpoints using Azure ML. You need monitoring. You may think that you need very specific ML monitoring, such as tools for data-driven detection, model-driven detection. But in most scenarios, all the metrics that you want to monitor related to your model are custom, and you can compute that following your own logic and then use common tools for monitoring, such as Prometheus and Grafana or ElkStack. And you need container registry, most likely, where you would store your Docker images that define your environment. And you need some tools for data version control or feature store. You can use Databricks for that, or Feast and Hopsworks. Those are also tools for feature store. So this is the full overview of MLOps tooling. But you shouldn't have a tool just for sake of having it. It is important to understand that tools are there to cover the MLOps principles. So version control, orchestration tools, and CD pipelines, they ensure code traceability and reproducibility and code quality. Model registry ensures model traceability and reproducibility. Feature stores and data version tools ensure data traceability and reproducibility, and container registry ensures environment traceability and reproducibility. But wait, what I covered, isn't it all just DevOps? The same tools, principles are overlapping. What's so special about MLOps then? So DevOps is a set of principles and tools that aims to shorten the development lifecycle and break the wall of confusion between developers and IT operations. So the idea is that the same people who develop the software must be able to maintain it in production. Well, the same is for MLOps. It has the same goals, but different parties are involved, and the wall is taller and thicker. So you have data scientists, machine learning engineers on one side, and you have the IT operations on the other side. In ideal scenario, the machine learning teams must be able to develop and deploy the machine learning models themselves without relying on other teams, or at least they should be provided the tools to do so. If we look at a software system, there are four main properties: code, data model, environment, and infrastructure. If these properties stay the same, it's guaranteed that the software system will perform exactly the same way. But it doesn't hold for machine learning projects. There is fifth component, which makes all the difference: statistical properties of the data. If statistical properties of data change, it may or may not affect your model performance. There is a great diagram by Outer Bounds, which shows the level of confidence in correctness of the system, depending on what system we're talking about. So for software engineering system, after local testing, after code reviews, and unit testing in the CI pipelines, we can be pretty sure that everything works as expected. But when it comes to machine learning systems, we never know for sure because the data may change any moment and everything will break. So far, we discussed generic MLOps toolings and MLOps principles and how MLOps is different from DevOps. But this course is about MLOps on Databricks. And guess what? Databricks has all the tools you need for MLOps as well. Let's walk through them. Databricks provides an orchestration system, which is Lakeflow jobs, previously Databricks jobs. You have experiment tracking, which is MLflow managed by Databricks. You have Databricks Compute, which can be serverless or all-purpose. You have feature engineering. You have model registry, which is also MLflow with Unity Catalog. You have model serving, feature serving, and model serving with feature lookups. You have lakehouse monitoring for monitoring. You have LLM observability. MLflow provides a lot of cool features for it, starting with MLflow 3. There is vector search, and Unity Catalog in general provides governance. There is another piece which simplifies deployment on Databricks significantly, which is Databricks Asset Bundles. Welcome to the second lecture of our free MLOps with Databricks course. In the first lecture, we discussed what MLOps is and why you should care about it. In this lecture, we're talking about developing on Databricks. First things first, this course is utilizing free edition of Databricks. If you Google for it, the first link you may see is actually referring to the free trial on Databricks. You should not use that one. Instead, you should use free edition, which is replacing Databricks Community Edition. Let's sign up for it. We fill in where we are located, so I'm in Netherlands, and we are going to continue and create the Databricks Free Edition. So I've proven I'm human, and we can go on. Awesome, we are in a completely new free edition Databricks workspace. You can actually see it's free edition because it says free edition under the logo of Databricks in the upper left corner. Well, we have the workspace now. What about the code? The code is located in our Marvelous MLOps organization, and the use case we'll be working on in this course is Marvel characters. Bashak and I are big Marvel fans, so when we saw this dataset on Kaggle, we couldn't resist. To be able to follow along the course, we recommend to fork the repo. In that way, you can also follow along the CI/CD part of our materials. So let's fork it. I will fork it under my own user. For you, it would be your own user. So let's create the fork. So here is the repo. Let's clone the repo. I will clone it in the Marvelous folder. So the repo is here. Let's open the project in the VS Code. Okay, so we have the Marvel characters project. Let's take a look at the project configuration file. Here we have defined different environments, production, acceptance, and development. And for each of them, we have a different catalog. So MLOps Prod, MLOps Acceptance, and Dev. And there is schema called Marvel characters in each of these catalogs. We have experiment names for basic and custom model, parameters for the model. We are going to train a light GBM model. We have numeric features like height and weight and categorical features. And we also have target alive. So we are going to predict whether the Marvel character is going to survive or not. The code wouldn't run unless the catalogs and schemas are created. Let's do that in the Databricks workspace. Let's create a catalog. We call it MLOps dev. Let's also create MLOps acceptance, and the MLOps prod at the same time. And now we need to create a schema called Marvel characters. Let's create it. We repeat the same thing for acceptance and production as well, so that we don't have to bother with it later. We could have automated that, but to get a feeling of how Databricks works, that's probably the best way for you to do it like that for now. So we have our MLOps dev catalog and Marvel characters schema. The next thing we need to do is installing Databricks CLI. I'm using a MacBook, so I will be using Homebrew, but use the tool that supports your operating system. I already have a Databricks CLI installed. I'm showing it for the purpose of showing it. Once Databricks CLI is installed, we need to configure it. We can authenticate towards Databricks using the Databricks authentication command. And we need to provide the host, and the host we can copy from the workspace. So that's the host with HTTPS in it. So we have created the profile. It goes back to Databricks to authenticate. And the profile was successfully saved. Let's go to the Visual Studio Code. Here I have Databricks VS Code extension. You can install Databricks extension by going to the extensions and looking for Databricks. I actually need to update it. So let's update it. Okay, so the Databricks extension is updated. By the way, it also works on Cursor if you prefer to use Cursor instead of VS Code. It currently says invalid host for the target dev. So what does it actually mean? We have the Databricks YAML file where the Databricks extensions knows what host you're using for different targets. We will not be going through the targets right now. It actually will be later in the lecture when we are going through Databricks deployments. But for now, the only thing you need to know is that you need to update your host to an actual value. Okay, so it is actually now connecting to the Databricks. We can check the configuration profile that was created in Databricks configuration file. It was created by us running the Databricks authentication CLI command. It actually shows us a lot of red signs, and what it expects from us is having a Python environment. Let's check out the PyProject.toml file. Here we specify the project name, we specify the Python version, we're using Python 3.12, and we specify the dependencies with its exact versions, so that when we install our private package, Marvel characters, all these packages are also getting installed with this specific version as stated here. We also have optional dependencies of the project, which we use during the development. And these are Databricks Connect, IPyKernel, we also need pip, and the pre-commit, so that we can check that the code quality is according to the standards defined as well here in the PyProject.toml file for the RAF tool. Let's now run the uvsync command, and because we are in development mode, let's also install the optional dependencies. uvsync extra dev. As simple as that. It's creating also the virtual environment, and we want to select it for the workspace folder. It now shows that the active environment is Marvel characters and we don't have any cluster attached. So let's actually use a cluster, and in this case we want to use serverless. That's the only option we have when we use Databricks Free Edition. So I just restarted the terminal and I now have a correct virtual environment showing up here. Let's do the following thing. Let's go to our Databricks workspace, Free Edition, and the one way to interact with our code base is using Git folders. So we can create a Git folder here, and the only thing we need to do is pass this name of the repo and create a Git folder. Our friend wants to jump, and we're not letting him jump this time. Let's go to the notebooks folder and let's take a look at the Lecture 2 Marvel Data Pre-Processing Notebook. The first thing we need to do is set up the environment. We have environment version 2 set up here by default, but we need to have environment version 3, which matches our Python version. You can read about different environment versions in Databricks documentation, and there are in total 3 different environment versions. Environment version 3 is the most recent one, and end of support date is in June 2028. If we go to the environment version, we can read the specifications of it. And we can see that operating system is Ubuntu 24.04.2 and Python 3.12 and Databricks Connect 16.3. And there are some installed Python libraries already. It doesn't mean that you can't install other versions of the libraries on top of that. That's exactly what we are doing. Environment version 3 is very similar to Databricks Runtime 16.4 LTS, but it's much more lightweight. The runtime comes with operating system, the same one. It also comes with the same version of Python, but on top of that, it also has Java, Scala, R, and Delta Lake. Databricks runtime can be selected for job compute or all-purpose compute, interactive clusters, but those are not supported in the free edition. In free edition, you can only use serverless compute. So let's go back to the notebook and let's apply the environment version 3. You can't really choose many things for serverless compute. The only thing you can really tweak is the memory, and there are not so many options available. It's either standard or high, and auto-scaling is defined by Databricks, and all other options are defined by Databricks, and you can't really change it. Serverless compute is great for running SQL commands or for low memory intensive applications, but some machine learning projects require quite a lot of memory, especially if you are using the pandas command for your light GBM or other models. It will all run not in a distributed way, but in a single node, and it will require all the memory you have. For this specific project, we don't really need a lot of memory, so we just select the standard memory option and let's apply the environment version 3. Okay, so the serverless compute is connected now, and let's install the libraries that we have as dependencies. It basically takes requirements from the PyProject.toml file and just installs all the dependencies mentioned here with the versions we specified. Okay, well, let's start and try to import the libraries that we have. And it can't find module named Marvel characters. So the solution for that is not really great. We need to adjust the system path. I don't recommend doing that ever. Please don't do that. But there is no way around it in a Git folder. So we can see that this code runs successfully. The Marvel characters package could be found, and then we can also import some modules from that. I'm not going further with this notebook in the Databricks workspace, and instead I will show you a better option. So let's go back to our VS Code. And let's talk about the project a bit more before we go and deep dive into the code. So this is the dataset from Kaggle, where you have information about the name, universe, identity, gender, marital status, height, weight, origin. I think it's pretty cool dataset, so I hope you enjoy it too. Just to be clear, this course is not a data science course, it's an MLOps course. So we're not really going to deep dive into how to make the best model. And obviously it's just a data set to play with, not really a serious use case. You may hear a happy cat sound in the background because Cat is on my lap and very happy that he is there listening to this lecture. So now I will be going through the Lecture 2 Marvel Data Preprocessing notebook, and I will run it in the VS Code. You can notice that there are separate cells that you can run, and you can do that because there is a VS Code setting specified here saying that this is an interactive Jupyter Notebook cell. You could put anything else in there and make anything else an interactive cell delimiter, but that's a default Databricks setting. We don't have to run these cells because we actually have an active Python environment with all the libraries that we need. So we can start right away from here. So we are loading project configuration. So let's take a look at the Marvel characters configuration module. Well, in fact, it's pretty simple. We are using Pydantic to validate the data types. And in that way, we ensure that whatever is put in the configuration file is actually correct and can be used later in the process. The next step we do is creating a Spark session. We will not be using it right away. In fact, we are using the local dataset stored in the data folder. But we will use it later to upload the data to a Delta table in Unity Catalog. So let's run this cell first. What happened here is just reading a pandas data frame. And then we are using the data processor class. Let's take a look what that is doing. Let's go through the data processor class of the data processor module in our package. It gets initialized with pandas data frame configuration and the Spark session. The first method, preprocess, doesn't take any arguments, but we need categorical features, numerical features, and the target. We rename some columns. We take universe feature, and if the value is unknown, we fill it with unknown value. Then we don't want all the universes to be present because it creates the noise. So we only want most common universes like Earth 616 or Earth 199999 to be there. And small universes will have value other. We also don't want to have value of the teams that the character belong to. We just want to know whether the character belonged to a team or not. So, for example, if Marvel character was a member of Avengers or X-Men or maybe both, we don't care how many teams. We just want to know whether the character belonged to any team or not. We also have origin. Origin means whether it's a human or mutant or anything else, and we will fill unknown values with unknown. We also have identity, which is public, secret, or unknown. We also have gender. So we fill unknown values with unknown, and we will define male, female, and other as a gender. Then we look at the marital status. We want it to be in unknown, single, married, widowed, and engaged. Then we create features magic and mutant. If origin had magic word in it, then we set magic to 1 and otherwise to 0. Mutant, if there was a word mutant in origin, we assign it to 1, otherwise to 0. And then we also normalize origin because it had many different values. So if human is in the string, then we return human. If mutate or mutant was in the string, we return mutant. So human is more important than mutant here. Then if Asgardian, then Asgardian. If alien, then alien. We do the same for symbiote, robot, and cosmic being. And otherwise, we return other. In that way, we try to reduce noise as much as we can. And then we look at our target variable alive, and we only keep values alive and dead, because there are some weird values out there as well. And the resulting data frame will only have numeric features, categorical features, target, and page ID, which is a unique identifier of our record. So then we have split data method, which takes a test size and random state, and we use scikit-learn function for doing train task split, and return train set and the test set. And then we save train and the test set to catalog. And then we also enable change data feed. So this is how the data processor looks like. And let's go back into the code. So let's run the cell for the data pre-processing. We split the data into the train and the test set, and then save data to catalog. Here we're actually using Spark session, and it's actually writing data to a Delta table in Unity catalog as we speak. That's actually interesting why Spark session works, because if we are doing uv pip freeze command, there is no PySpark. It's just not there. So why does it actually work in the first place? Because we're using Databricks Connect. So if we look at our PyProject YAML file, we are using Databricks Connect, and Databricks Connect actually comes with PySpark embedded into it. And that's why you should never install PySpark together with the Databricks Connect. It's gonna have conflict with each other. So let's go and actually check whether the data is there. And we can go to catalog. We go to MLOps dev. We go to Marvel characters, and yes, here is our train and the test set. It's pretty amazing. That's all what we did from the VS Code. We used DB Connect to upload the data to Unity catalog. There is one more thing I wanted to mention. There is pretty cool feature in the VS Code extension that is called Remote Folder. It actually lets you upload all the files to Databricks by just clicking this button. So you can see that it's actually synchronizing all the files to a workspace. We can go and check whether it's there. So it's in the workspace, we have a bundle folder, we have dev, Marvel characters, files, and here are all the files that we just synchronized, which means you can go to a notebook and actually run the notebook from here as well, if for some reason you can't run the notebook from the VS Code. And there are multiple reasons why you couldn't be able to. So for example, some commands like delta table commands wouldn't work from your VS Code. Also, feature engineering package wouldn't work from the VS Code, and you would have to execute it in a Databricks environment. Let's run a UV build command. And in that way, we are actually going to build our package, and it is stored in the dist folder. Just copy paste the name. The dist folder is in the gitignore file, and therefore it will not be synchronized to Databricks Workspace. You also see that there is nothing going on here. There is no synchronization of the dist folder. But instead, let's just copy paste this Marvel character wheel to a notebooks folder. Let's just move it there. And we can see that the wheel is uploaded. So we can go to the notebooks folder and we can see there is a wheel file there. And let's go to this notebook again. And instead of running all these commands with pip install -e and adjusting the system path, you could just pip install the wheel. We don't use the right environment here, so it's also convenient to still do that because it will otherwise fail. But then you can just pip install the wheel, and this might be a more convenient option for you to deal with the Python packages. Welcome to the third lecture of our free MLOps with Databricks course, and I will be talking about getting started with MLflow. The main focus of this lecture is experiment tracking, and in the follow-up lecture, I will talk about logging and registering models using MLflow. Let's talk about the MLflow components first. MLflow tracking is a centralized repository that logs machine learning models and the parameters, metrics, and artifacts. Model registry is a centralized model store that allows to manage model lifecycle, add tags, aliases, and new model versions. There is also MLflow Evaluation, a set of tools to facilitate model evaluation for Gen AI applications and also for standard machine learning. And there is also MLflow Tracing that enhances LLM observability in your Gen AI applications. Experiment tracking and model registry have different backends. Experiments can be found in a workspace, while models are registered in Unity Catalog. There is also the old way of registering models in the workspace, but it is a legacy, and we are not going to cover that. Experiments in MLflow are the main unit of organization for ML model training runs. All MLflow runs belong to an experiment, and each MLflow run corresponds to a single execution of model code. All MLflow runs are logged to active experiment. MLflow experiment can be created by using MLflow create experiment or MLflow set experiment commands. Let's now deep dive into the code. I will be covering Lecture 3 MLflow experiment tracking notebook. We are running it in the VS Code, so let's start with running the cells. In this lecture, I'm going through Lecture 3 MLflow experiment tracking notebook. Let's start by running the first cell. There is a function called isDatabricks, and it's checking whether there is Databricks runtime version environment variable is present. It is present if we are running code on Databricks, but we are running code locally, so we don't have it set up. And the tracking URI is also set to the local file path. That's actually not what we want. We want to use Databricks MLflow instead, which must be pointing to our workspace. We have a trick for that. We are using the load.env function, and what it's doing, it's taking our .env file where we specify the profile, and it uses the value specified here as an environment variable. Why do we set this specific profile? Well, that's a profile that we use to authenticate to Databricks. We can go to this Databricks configuration file, and we have a default profile which is empty, and we have profile with this name that is specifying what host it's using. So you can notice that the tracking URI must be Databricks / and the profile name, and we also need to set registry URI, even though we're not using registry yet. Starting from MLflow 3, it's also important to use this command even if you're just doing experiment tracking. So let's run the command, and we can see that we have the correct tracking URI now. Let's set the experiment. So we create a new experiment called shared Marvel demo, and we also set experiment tags, repository name, and our repository name. And that's an experiment that we see here. I wanted to show you how you can inspect any Python object by dumping all the attributes in a JSON file. So we created a folder called demo artifacts, and I'm using JSON lens to look at it. So let's use the light mode, and we can see that there is experiment ID, there is a name, there is artifact location, which is Databricks. We have the lifecycle stage, we have creation time and the end time. We have the owner ID, source name, email, and the experiment type. That's how the experiment object looks like. We can get experiment by experiment ID, so we'll get the same object back. But we can also search for experiments. You can search using different types of filter strings. So for example, we actually set a tag before, and now we can search for experiment using the tag. And since we just had one experiment with that tag, it just finds it. Let's start MLflow run. We can start a run using MLflow start run command. It's pretty straightforward. And it will create an active run. We can get the active run and see its attributes. We have the run name, we have the artifact URI, we have the source name, source type local. We are running it locally. But if we were running it using a Databricks job, it would actually specify the job where it's coming from. Or if we're doing it in a notebook, it would specify a notebook here instead. Well, let's end the run, and there is no active run anymore. So the active run is none, and it's true. So experiment now can be found on Databricks. Let's go there. And this is the run that we have. Well, we didn't log anything really. We also don't have any artifacts here, so it's logical. We didn't do much. Let's start the run called Marvel Demo Run, and we pass git sha to it. It's actually pretty useful because we can track different experiment runs based on the git sha. And right now we hard coded, but we can pass a real value to it, and that's what we're gonna do in the lecture about deployments. So here we log parameters and log metrics, and because we use the with clause, it ends the run as well. So you can see that there is no active run. Let's view the experiment again, and we can see that we have metric now, the metric 1, metric 2, and we have parameters, exactly what we logged. Let's try to get the run information. So we save the run ID into a variable, And we can now get the run by run ID, and we have run info. It's a lot of stuff in here. And again, let's dump it into a JSON file and review how it looks like. We have info, data, inputs, and outputs. Info contains artifact URI, end time, lifecycle stage, experiment ID, run ID. That's not a Databricks run ID because we don't have any. It's just a MLflow run ID. We have run name, start time. We have metrics and parameters, and we also have tags. Some of the tags are created by us, but some of the tags are created by Databricks. And depending on where you run your code, whether it's from a local machine or inside Databricks environment, it will create different tags. It will also create a tag if it runs in a Databricks job. What job did it come from? Now we can print run info data metrics and run info data parameters. They are part of this run info dictionary. And we can also search for run just as we search for an experiment. Let's try that. And we have this run back. And there is just one run because we didn't have, because we just filtered for the first one. That's what we did. But there are probably more of them already because I ran it multiple times. So let's start the run with the run ID. Basically, we are reactivating the old run. And let's try to add some information to it. So for example, we are now trying to log parameter type, which we already had. So we already had Marvel demo, and now we are setting it to Marvel demo 2. And we can't do that because that value is already there, so it's supposed to fail. A funny part, it actually fails in the VS Code, but when you do it in a Databricks notebooks, it doesn't fail, but it also doesn't actually set the new value. That's a good thing. So you can't overwrite it later if you want to, but you can set new things. So let's set a new parameter, purpose get certified. By the way, it really will help you to get certified for ML Associate or ML Professional Databricks certifications because it covers a lot of MLflow pieces. So we can view our experiment again. And we can see that now we have a purpose parameter. We didn't have it before, and now we do. And that's what we did with reactivating the run and adding a new parameter. You can also add new metrics or other things that you like. Let's start another run and log other things. So we start the run with a run name Marvel Demo Run Extra, and we will log metric 3. We'll also log a metric under the same key but with different steps. We will log artifact MLflow meme. You can see the meme. It's amazing. It's Marvel themed, obviously, just as we like. And we will also log text, dictionary, and artifacts. So we just log the whole folder that we just created. So let's run it. And we started the run, but we didn't end the run yet. So because we haven't finished logging things. So let's log a figure. Let's plot, let's log images. And now we ended the run and we can go and look at the experiment. And this is the run we created. And we have metric 1 and metric 3. We have a model metric that is displayed here, and you can see it per step, just some random stuff really. We can also see artifacts here. So we have the whole folder, demo artifacts, and we have images. So these were dynamically created. We have our meme in two places because we log the whole folder, but also the meme separately. And that's how we can find all this information. And it's not just we can find it in the UI, we can also download it back if you want to. So we can search for runs. Just as we can search for experiments, we can search for runs in way more complicated ways. So filter strings support a lot of different ways of searching for things. You can search by metrics, tags, run names that have certain pattern. So we can try to search for the run, and let's see what the runs is, and has this one record and that matches this profile. Now we have all these runs, we can load the dictionary back, the one that we logged. We can load the image. We can download all the artifacts. Let's do that. And we got a folder, download artifacts, with all the artifacts. Pretty cool. And the last thing I wanted to show you is a nested run. It's very convenient for hyperparameter tuning when you are looking through a lot of different hyperparameters and you want to log all the information about the runs and then search for them. That's how you do it, and that's gonna all be in one place. So let me run this cell. We're not going to talk about hyperparameter tuning here, but the idea is the same, that everything is presented in the same place. So let's go to the experiment again, and we have this top level run and stub runs that belong to it, which makes it easier to search for them. This is lecture 4 out of 10 of our free MLOps with Databricks course, and I will be talking about the login and registry model in MLflow. Let's start with the definition of MLflow model. MLflow model is a standard format for packaging machine learning models. It provides flavors as wrappers for specific machine learning libraries, which ensure consistent saving, loading, and inference deployment for models from diverse libraries. If you want to write some custom code, then you can use Python, which uses Python model base class. In this video, we will be going through both scikit-learn model flavor and the Python model flavor, and we'll look into MLflow model definition in detail. Overall, MLflow supports a lot of different model flavors: scikit-learn, Profit, LightGBM, LangChain, OpenAI, and many more. Let's dive into the code. Let me first walk you through the train register basic model notebook. We start by importing all the libraries, I already did that, and defining whether we are running on Databricks by checking whether Databricks runtime version is there. It's not there because we are running it locally, so we would need to use our .env file where the profile is specified to define the tracking URI and register URI and set it. That's what we did in the experiment tracking part as well. And then we load the configuration file, we set up the Spark session, and we define tags, which are some random values here now, but in the real deployment, we'll be taking these values from Git and pass it to the code using Databricks asset bundles. Let's run this piece now. Then we initialize model. We pass configuration, tags, and Spark session. Let's take a look what that basic model class is doing. So indeed, it takes a configuration and a Spark session, and we set some attributes like numeric features, categorical features, target, parameters, catalog and schema name, experiment name, model name, and we set tags. We make a dictionary out of it because that's how we can pass it to a run or to registered model. Then we load the data. So we already saved data to a train set table and a test set table previously when we were looking at the pre-processing step. And we need a Spark data frame and also Pandas data frame, because that's what LightGBM model requires, and that's the model we are going to use. We have Xtrain, Y-train, X-test, and Y-test, and we have evaluation data, which is required later for MLflow evaluation step. And then we define what version of the Delta table is used for training and testing purposes. We use the Delta table from the Delta package for that. And we are looking at the history and selecting the very last version here. Then we prepare the features. In the prepare features tab, we defined our own custom transformer. Well, the reason why we put it inside the other class is because we don't need to deal with private packages otherwise. So it was an easy fix. But later, when we are going into the PyFunk, I will show you a proper way of dealing with this kind of dependencies. So this custom transformer has fit transform, and transform methods. So the fit transform learns from the training set what categories are present there for a certain feature and transform these categories into integer encoded categories. And at the transform step, if the category value wasn't seen previously in the train set, it will assign value -1. So the pipeline, the scikit-learn pipeline, consists of two steps, the preprocessor and classifier. And the preprocessor uses column transformer and it takes the transformer which we just defined as a transformer input. The LightGBM model can deal with integer encoded categorical values, and it often performs better than one-hot encoding, and that's why we implemented this custom transformer here. Then we have the train step, which is just pipeline fit on the Xtrain and Y-train. And then we go into model logging. Here we set the experiment, we start the run, and we pass tags we defined earlier to the run tags. And it will make it possible to search for runs that belong to certain code version. Then we define model signature. To infer signature, we need model input and model output, which is just Xtrain and pipeline predict on Xtrain. Then we define the train and the test dataset, and this train dataset is defined as MLflow data from Spark function, and we pass train set Spark, that's our PySpark data frame. We pass table version and table name to it, and the version was also defined earlier using delta table command. Then we can log input with context training, and we do exactly the same thing for the test set. Then we can finally log the model, and here we use scikit-learn model flavor for that. Even though we are training a LightGBM model, we are still using scikit-learn pipeline, hence the scikit-learn flavor is required. We pass the pipeline, we define the artifact path, which is just name of the folder, and it can be any name that you like and find descriptive for what you're doing. We pass the signature and we pass the input example, which is convenient to actually check how model predict function works, and you don't really have the input example anywhere else. You can just retrieve it from the logged object itself. And notice we don't log any metrics here, the model quality metrics, but we use MLflow model evaluate function instead, and it will log all the model metrics, which are default model metrics here, to the run. So we can always see what was the model performance. And we need to pass model URI, which is derived from model info and evaluation data, the target, model type, and what kind of evaluators you need. And we save these metrics from this result as attribute of the class. I will walk you through the registering model later, and let's go back to our code. So after we initialize the basic model, we will load the data and prepare features. Okay, so let's train the model now. And then we can log the model. So the model is now logged. Let's check it out, how it looks like on Databricks. Well, it's still not completely finished, but we can see the artifacts that were logged already. So that's the ML model. Here we have the artifact path. This model has two flavors. It always has Python function flavor, and it has a scikit-learn flavor. It specifies what MLflow version was used, the Python version, the model ID, how large the model is. We also have the run ID, so that's the MLflow run ID, which was used to log the model. We also have the saved input example, which is specified here, and the signature that we passed earlier. It also has conda YAML file. These are all the values that we can find in our PyProject YAML file. It inherited that environment here. We also have environment variables.txt, and this file records environment variable names that are used during model inference. This is not used by us, but it's inferred from the environment, and the MLflow logged it for us. Notice that it doesn't actually log the value itself, but just the name of the environment variable. So this is the model pickle file containing our pipeline. We have a Python env.yaml file, which specified what version of Python is used and dependencies. This requirement.txt is exactly the same as in conda YAML file. It may feel like there are a lot of different repeating values, but that's just how MLflow works. And we also have the serving input example, which has this data frame split, columns, and data. And this can be quite convenient to call the endpoint later. And we can see that the status of the model is ready now. And we also have the data sets used and metrics recorded. So these are all the metrics that we haven't recorded ourselves, but it was created using MLflow evaluate. And we have the accuracy score, the recall precision F1 score. I think it's not that bad for predicting who will die in Marvel universe. Well, let's actually check some examples of these kind of characters just to visualize. So we all know Natalia Romanoff, Black Widow. Any Marvel fan knows her. So Earth 199999, that's our Earth in Marvel universe, and we can see that she has living status deceased, and indeed she died on Vormir. And there is also Natalia Romanova from Earth 616. That's a different universe, because we have to deal with Marvel multiverses. And Natalia Romanov here, she actually is not deceased. So she is alive, but she was resurrected. That's interesting to see that kind of the same characters with similar characteristic, depending on the universe and the origin, they can have different living status and, well, different storyline really. So let's go back to the code. We looked at the logged model in the UI, but you can also get the logged model using the model ID. So this basic model info, which is an attribute of our basic model class, we can get this logged model here. And we can also load the model using the model URI so we can see what this model actually looks like. That's exactly the pipeline that we logged. Let's now inspect the logged model class by dumping its attributes to a JSON file and view that using JSON lens. It seems like a very large object, but in fact on the top level we have artifact location, the timestamp, experiment ID, when it was last updated, and most of these things belong to metrics, which are metrics logged using MLflow evaluate. Then we have model ID, model type, name, source run ID, status, and tags. Tags have Databricks cluster ID, artifact location, model name, source type, MLflow user, and the artifact SPN. So the tags that we pass to it actually not there, but they are in the experiment run. So we can always find it back. So the log model can be used to retrieve parameters, which we haven't logged, and metrics, which was logged using MLflow evaluate. So let's now search for runs. We want to find the run that we used to log the model. So it is there, and we can maybe view the model. So we load the model now, but in the URI we use the runs and run ID, but here we use just models and model ID. So these are two different ways of loading the model. Let's now get the run. And we can actually see that it has this git.sha tag that we passed before. Let's now load the training input and the testing input that we logged before. So this is the training input. It matches the exact Delta table version and table name. And the same we can do with the testing input. So this is our test data set. And once we finish with that, we can proceed with registering the model. So let's run the command, and in the meantime, check what it does. The registering model step actually registers the model, and we pass the model URI, the name, and the tags. Tags make it easy to trace it back to the code version that we were using. And once model is registered, we find it convenient to set up a specific model alias because you can search for model version by alias. An alias we set here is latest model. So the reason why we do it is because we want to retrieve the latest model version, and the latest alias cannot be used, but you also cannot refer to the latest model by latest alias. So the best alternative we found is just setting latest model alias. So let's go back to the code. You can only search model versions by name. So we have a MLflow search model version, and then we filter string by name. And this is what we will get. And we will get this model 2, version 2, and all the information about it. And you would think you can also search models by tags or other things. Well, you can't. This is an invalid parameter value. It's impossible to search it by tag. Let me walk you through the train register custom model notebook. It starts in exactly the same way by importing all the modules, by defining the tracking URI and registry URI, by loading configuration, setting up Spark session tags. But there is one difference here. We are looking for code path. That's a place where our Marvel characters package wheel is stored. We can get this wheel by running the uv build command. It will create the wheel file in the dist folder, and that's what we are referring to here. And we can get the exact version of our imported package by using import lib metadata. What we do next, we're using MLflow client to search for the latest model of the Marvel character model basic. We do that by latest model alias using the get model version by alias function. So our rep model version looks like this. And from the rep model version, we can get model ID, which allows us to recreate the model URI, which we will use to wrap our model. So here we are defining our Marvel character model custom model. First, we define the wrapper, this Marvel model wrapper. We create an instance of that, and it has log register model method, which takes the model URI, the wrapped model URI, the PyFunc model name, experiment name, input example, tags, and code path. Let's check out how this code looks like that defines this Marvel model wrapper. It is located in the custom model module under models in Marvel character package. So first thing to pay attention to is that Marvel mode wrapper comes from the PyFunc Python model base class, and it has load context method, which loads the context and actually loads the model. But what is it actually loading? So this artifact context is defined in the logging step. When we run MLflow PyFunc log model, we provide artifacts argument, which is a dictionary of artifacts and their locations. So here we call LightGBM pipeline is a key of dictionary, and the model URI is the value. So what we're doing here is we're loading the model using the model URI. Load context runs whenever the model gets logged, and it will package this artifact together with the PyFunc model. We will check out how that looks like in the UI a bit later. Then we always need to have a predict function. So what we're doing is we're using the predict function from the model. So this is the scikit-learn pipeline. And we need the model input here, which is pandas data frame on NumPy array. And the context always must be an argument in this predict function. If you don't specify that, it will fail at the inference step in model serving. So you always need to have the context here. And what we do, we return adjusted predictions. And just to demonstrate how to deal with private packages in MLflow, we have these adjust predictions outside of the model wrapper class, which means that the package itself must be available for the model serving endpoint later. And we have to package it together with the rest of the code and with the model itself. So we have the log register model step. What it does is sets up the experiment. It starts to run, and we specify the additional pip dependencies here, which is essentially code folder / the wheel name. And we provide that as conda-env. There is a function MLflow conda-env, and here we provide the additional pip dependencies. We specify the signature, and the output is a bit different here. So survival prediction alive. And then we run this MLflow PyFunc log model, where Python model is self because it's the class itself. Name is PyFunc wrapper, artifacts already covered, signatures, exactly in the same way as we did for scikit-learn, code path, and conda-env. And then we have the MLflow client, we register the model, and we also set registered model alias, just as we did for the basic model. Let's go back to the notebook and run the code. I already triggered the initialization of the test set, and logging and registering the wrapper. So we can view logged model here. The most interesting piece is in the artifact step. So we have a ML model here. ML model has Python function flavor. It doesn't have scikit-learn flavor anymore. It has a Cloud Pickle version, artifacts definition. We can see that model URI of the wrap model is present here with the model ID. So we always know what model was actually used. Then we have the Python version, a MLflow version, and the signature. We also have conda YAML file, Python environment YAML file, the pickle, so the model itself, and requirement.txt. And we have two requirements here, the MLflow version and code Marvel character, which actually contains all the requirements that we need. And this is the wheel. It's located in the code folder. So it is actually part of the packaged model, and it will be available always at the serving step. And here we have artifacts, and this is our basic model that has this Python function flavor, scikit-learn flavor, and all this information that we logged together with it. So essentially, at the logging step, it downloaded the model from the model URI and wrapped it and put it in the artifacts folder. That's what happened. So this model was also registered as version 2 because I was also running experiments before and registering model before. So this is where the registered model is. It points to the Unity catalog model version. And that's all the information we have about it. We have the signature, we have information about model version as well, and we can see whether there is any active serving endpoint. So let's now load the model that we logged and registered. We can do that using latest model alias, and we can unwrap it and run predict on that. So the unwrap model predict runs successfully, and we have our survival prediction alive output. The reason why you want to have the unwrapped model is because you can access all the attributes of the original custom model, such as model, which is a pipeline that we wrapped. And so this is the scikit-learn pipeline that we previously had, and it is available as an attribute because it got initialized at the logging step. We don't always have to do that. We could just take the loaded PyFunc model and run prediction on top of that. So let's try. So predict, and we don't have to pass context either. We just need to pass some observations, and we have the same output right there. So that's all great. It works locally, it works on my machine, but it doesn't guarantee that it will work when we move to model serving. Why? Because here I already have an established environment. I have all the packages imported that I need to run this prediction. But when we go into model serving, this environment must be initialized. And the only way to know for sure that everything works is using this function. We have this MLflow models predict. We pass the model URI and the observations. This doesn't work locally, unfortunately, so we need to run it on Databricks. I already ran it for you because it takes 5 minutes, so just demonstrate what I did. I synced all the files that I have in my VS Code. As I was showing lecture 2, I specify the environment version here. I install all the libraries, so this Marvel characters package, restart Python, I import everything I need, set up everything I need, and then I can just run this function. It took 5 minutes or so to run. And in the end, we know that this would work for model serving endpoint. This is lecture 5 out of 10 of our free MLOps with Databricks course. And I will be talking about model serving architectures. In general, there are two main model serving architecture patterns. The first one is batch serving. Batch serving means that all predictions are pre-computed and stored in a database, and machine learning endpoint simply reads the prediction from the database on request, and there is no computation going on the machine learning endpoint side. Typical use cases can be personalization or recommender systems when you compute these recommendations in a batch fashion once per week, and then when the customer logs in, he will get these recommendations from the database. A second scenario is real-time model serving. It means that machine learning endpoint is computing predictions at the request. It also can be so that it reads some of the features from the database and some features are available from the payload. Typical use cases can be fraud detection, also recommender systems, but also use cases like dynamic pricing. Let's now talk about these architectures on Databricks, how they can be implemented there. Let's take a look at feature serving first. In the most simple scenario, you have a Lakeflow job that roughly consists of 3 steps, which is data pre-processing, model retraining, and generation of predictions. It can also be 2 jobs instead, that you retrain your model once per week, but you generate predictions daily. And then, after predictions are generated, we write them to a feature table. This feature table cannot be used directly behind a model serving or feature serving endpoint. We need to have an online store. It can be Databricks online store, which is using Lakebase on the background, or it can be an external online store like DynamoDB, which also integrates with Databricks if you use AWS. In the end, we need a feature spec, which is treated like a model by Databricks. And this is what is being served behind a feature serving endpoint. Feature spec is a combination of feature lookups and feature functions which define how we return features back. We can look them up in an online store, but we also can do some basic calculations using Python or SQL. And in the end, an application is sending a request to this feature serving endpoint and getting response back. Let's take a look now at the second scenario, model serving, which is also a very simple scenario similar to feature serving. That's what we are going to serve in this course. We are going to serve the custom model that we registered earlier. In the case of model serving, we have a Lakeflow job that does data pre-processing and model retraining, and in the end, we register model in Unity catalog. After the model is registered, it can be directly used behind a model serving endpoint because we are not looking up any features and all the features are available through the payload. So the app can send the request to model serving endpoint and get a response back without looking up anything anywhere. Model serving with feature lookup is the most complex but most realistic scenario when we have 2 different Lakeflow jobs. One is to do data pre-processing. In the end, we update the feature table in Unity catalog, which is used by another job to do model retraining. The schedule for these 2 jobs can be different depending on how often the features must be processed and how often the model must be retrained. The feature table is used to create a training set to retrain the model, and then we can also log the model and register it in Unity catalog. However, in this scenario, model logging is using feature engineering package on Databricks. The feature table that was updated using the data pre-processing job also must be synchronized with the online store. similar to the scenario of feature serving, which we covered earlier. And the model serving endpoint needs to have a registered model behind, but also at every request, it needs to look up features in the online store. You don't have to set anything up, it's all done by Databricks using the feature engineering package. It creates a PyFunc that we can't really control, and in the end, model serving endpoint can be queried by the app and will return response back. So far, we walked through these three different architectures, but when should you use one or another? If you have a model artifact and need predictions to be computed at the moment of request, you need to use model serving. If you have a model artifact but not all the features are available through the payload and need to be looked up in the online store, you need to use model serving with feature lookup. If all the predictions are pre-computed and you just need to serve them, you need to use feature serving. If you need to compute a simple function that doesn't require model artifact, you could also use feature serving, just using feature function behind it.
This lecture, we will cover deploying model serving endpoint. But first, let's have a look at what we have learned so far. We started with fundamental MLOps principles, what tools and functions Databricks offers us. Then, we have seen some best practices on how to work locally while developing ML applications with Databricks. And then we moved on to MLflow basics, how to train, log, and register models in Unity Catalog. Last lecture, we showed different serving architectures. If you haven't seen lecture 4 yet, you may want to check it first as we will start from where we left in that lecture. In lecture 4, we have registered a basic model, MLflow model, which has built-in flavor, and then we registered a custom MLflow model using PyFunc, which gives us the flexibility to implement any logic we want or change the payload. So this lecture, we will deploy an endpoint for the models that we registered, send some example requests, and then see an example of A/B testing. Both models registered in lecture 4 can be served using model serving module that we will introduce today. But first, let's start with theory. Databricks Model Serving is a fully managed serverless solution that allows you to deploy MLflow models as RESTful APIs without the need to set up or manage any infrastructure. It is super easy for deploying registered MLflow models. It has automatic scaling even all the way down to 0 when there's no traffic. It comes with built-in monitoring directly in the Databricks UI, where you can track latency, throughput, and error rates. And it supports both batch and real-time inference. It makes the transition from experimentation to production very smooth, and it is ideal for teams who want to focus on building great models without getting bogged down in infra concerns. And since it integrates directly with the MLflow model registry, everything just works out of the box. But it also comes with some limitations. First, you cannot choose the runtime environment. Databricks handles that for you. This can be a constraint if your model depends on a specific library version or runtime behavior. Second, you have no control over the underlying cluster size. For example, a single replica is limited to 4 GB of RAM, which may impact large models or requests that require more memory. That said, you can choose the workload size, which determines the number of compute units allocated per replica. Databricks offers small, medium, large, and on request, extra large options like XL, 2XL, 3XL, scaling all the way up to 512 units for more demanding use cases. Additionally, if you enable scale to 0, the serving endpoint can scale down to 0 replicas when it's idle. The lower bound for each workload size becomes 0, which helps save cost in environments where the usage is intermittent. Let's look at some compute units and performance limits. Each compute unit in Databricks Serverless Serving can handle one request at a time. So if you receive multiple concurrent requests, multiple units will be needed, even if each unit is underutilized in terms of CPU or memory. Databricks uses auto-scaling based on unit demands, not based on CPU or RAM usage. This means even if a unit is only used, let's say 5% of its CPU, Databricks may still scale up if more concurrent requests are coming in. The number of units needed is calculated using a very simple formula. Required units is equal to query per second times model processing time. Let's see this in an example. If you're serving 1000 queries per second and your model takes 20 milliseconds per request, that's 0.02 seconds, then you will need 20 units to keep up without delay. And there is a hard upper limit to this. A maximum of 512 units can be allocated per endpoint and per workspace. So the maximum achievable QPS at 20 millisecond latency would be around 25,600. Databricks is using MLflow behind the serverless endpoint, and it supports different dictionary payload structures, which you can see in this table. And we will also see some examples in our code base. Now, let's create serverless endpoint using custom model that we registered in lecture 4. This is my VS Code, and I open my repository. I am connected to my Databricks workspace through VS Code extension, which actually uses DB Connect. I'm using serverless cluster, and I activated my Python environment. So I have a good base to start. So far, we have covered several lecture scripts. In this lecture, I am walking you through Lecture 6, Deploy Model Serving Endpoint. This will be our main entry point. We are also introducing a new module, which is Serving Model Serving class. This will give us some functions that we will run from our main script. For this code to run locally, we also need to make some environment variables available. So in my .env file, I define Databricks token and Databricks host, which are must to have. And I also have a profile, which is optional unless you use default profile. Let's get Databricks token first from our workspace. We are in the workspace and we need to go to our settings, profile settings. Under profile, you will see a developer section. Here you can manage all the accesses because you are the admin of your workspace. And here you can simply generate a new token by giving a name and hit the generate button and it will give you a new token. You can simply copy this and paste it to your environment file. Now I define all the environment variables. Let's start running the cells. I start with importing all the libraries that I need, including my custom modules from model serving class. And next I get the environment variables. If this is running in Databricks environment, DBR token is available through dbutils, and Databricks host is available through Spark config. But I am not in the Databricks environment, so I simply get it from my .env file. Next, I create the model serving instance by passing some variables: the model name that I want to serve and the endpoint name that I want to create. I initialize this model instance. Now I will run deploy and update model serving endpoint. But let's have a look at what this model serving class offers us. This is the class where we wrap all the logics that we need to deploy an endpoint. We define a getLatestModel helper function, which retrieves the latest model version of a given model name. It is using MLflow client and getModelVersion by alias function. And then I have deploy and update serving endpoint. First, we check the endpoint if the endpoint already exists. We do this by listing all existing serving endpoints in our workspace and seeing if one matches our desired name. If the user specified latest as the version, then we fetch the actual latest version using our helper method getLatestModelVersion. Otherwise, we just use what they are passed in. Next, we construct a list of entities to serve. In our case, just one model. We specify the model name, the model version, and the scale. And finally, we check if the endpoint already exists. If it doesn't, then we create it from scratch with the given config. If it already exists, then we update its configuration to point to the new model version or change parameters. So let's go back to our main entry point and run model deploy or update model serving endpoint. In my interactive cell output, I see that the latest model version is 2. The very first time when you create a serving endpoint, it will take 5 to 10 minutes for endpoint to be ready. Since I already created this one, it says ready, so I can create some sample records and hit the endpoint. Let's do that. I'm back to my notebook. I create a sample set, sample records to be used in the payload. I use the test set to create my sample records. Here I define the required columns, which are the features that my model expects. Another trick I have to do here is replacing none values with none, which will be serialized as null in JSON when we send the payload to the endpoint. And here is you see an example data frame record in the request body as a list of columns and values. Here I define a call endpoint function, which calls the model serving endpoint with a given input record. It takes the host name from environment variables, and then it creates the serving endpoint name. This is the serving endpoint name that we just created. And then it simply sends a post request. So let's run this and wait for the result. Since my endpoint is configured to be scaled to 0, the first time when I hit the endpoint after creation, it will take some time to actually spin up the nodes because it was scaled down to 0, now it is coming back. But the next calls will be much faster. There you go. We get the response status 200 and this response text. If you want to send more requests in a for loop, you can also simply run the cell, and then you will keep seeing the responses from each call. While this is running, let's also look at our serving UI. Here we see the entity that we are serving and its version. We also see the workload size, which is small. And these are the monitoring dashboards where you can see the request error rate, CPU usage, latency, etc. This is how it will look like when you send more requests to this endpoint. Another important thing to do already is enabling inference tables. By default, the inference table is not enabled. In order to enable inference tables, you need to click Enable Inference Tables, define your table location, and hit Update button. So for me, it's already enabled, and this is the path to the table where I can see the logs of my payloads. Databricks model serving endpoints support traffic splitting. You can go to Edit section and list all the entities that you want to serve. You can also assign different percentage of traffic to each entity. You can configure this on the UI or you can use the SDK. But the split is random. And because of its non-deterministic behavior, we don't really recommend using it, especially not when a consistent routing is needed for A/B testing or user-level model selection. So now we're going to see an example of A/B testing in a deterministic way. Let's quickly remember what A/B test is. A common misconception is that simply splitting traffic between model versions qualifies as A/B testing. But that is not accurate. In true A/B testing, a customer must consistently see the same model version throughout the entire experiment. This consistency is critical to accurately measure model performance differences, whether it's a click-through rate, conversion, or other metrics. A naive traffic split, like Databricks build and traffic routing, doesn't guarantee this. One user might hit model A on one request and model B on the next, especially if the requests are stateless and routing is random. To run reliable A/B tests, you need a sticky assignment strategy, like a hash-based split on a stable identifier, could be user ID or session ID. That way, each user consistently gets routed to the same model variant for the entire test period. In our example, we will use two different versions of an MLflow model, and they will be combined into a main PyFunc model that serves as the core model for our endpoint for A/B testing. Now, let's see an example A/B testing implementation. For this part, I am walking you through Lecture 6 abtesting.py notebook. We are also going to use the basic model class that we have seen in Lecture 4, which has all the logics implemented in it: loading data, preparing features, training, logging, and registering model. We will use these functions in our A/B testing module. I start with loading my imports, which initializes the interactive session. Then I create Spark session, load my environment variables. I get the config. Here are my catalog name and schema name. And in the next cell, we are going to create a basic model, which will load the data, prepare features, train, log the model, and register a latest version. Here we see the output. It is taking a while. All right, we have the experiment. And we registered the model. Let's have a look at our workspace. Okay, this is the experiment that we just executed. And let's go to catalog, MLOps dev, catalog, Marvel character schema, and the models. All right, we just registered version 6. Nice. Let's now create a model B, which will use a separate parameters, different parameters. This will be our model B. It is following exactly the same logic: loading the data, preparing features, training, logging, and registering model. This time, we are registering Marvel characters model basic B. So this will be the name that we will see in the UI. We are seeing all the outputs written here. All right, the experiment is there. The UI can be flickering sometimes. There you go. This is the experiment we just executed for our model B. And we also just created version 1 of model Marvel characters model basic B. Let's check it out in our catalog. Marvel characters, there you go. We just created Marvel character model basic B and registered version 1. All right. What we are going to do next is what I showed you in the slides. We will define an A/B test wrapper, which will take model A and model B as an input, and it will use both depending on the ID. In the predict function, we are defining which ID should be routed to which model by using simply a hash function. It works by taking the ID from the input data, hashing it using MD5, and converting the hash into a number. Then it checks whether that number is odd or even. If it is odd, it uses model A. If it is even, then it uses model B. This way, the same ID will always be routed to the same model. We also remove it from the model input because the model does not need the ID. So this is a predict function that we define in A/B test wrapper. In the next cells, we are going to register this model. Let's start with loading the train and test set. Here we create an experiment. We pass the model name, create the wrapper model instance, and we start the MLflow experiment run. This will take model A URI and model B URI as an input while loading the context. Once this experiment is completed, we will create a new model and a new model version for the given model name, PyFunk Marvel Character Model AB. Here we see in the outputs that we just created version 1 for model Marvel Characters model PyFunk AB test. Let's click this and see in the UI. There you go. In my Marvel Character Schema model section, I just created a new model for A/B testing and a new version. The next is we will create a model serving endpoint for this specific MLflow model using the workplace client. It has the same logic as we've seen in model serving module. We define the serving entity, which is just one model, and this is the model endpoint name that we pass in the config. Since we already run this, we should be able to see in the UI that our endpoint is getting ready. There you go. So this is the endpoint we just created. And as I mentioned earlier, it will take some time to make this endpoint ready. My endpoint for A/B testing is ready. So now I can create some sample records and hit the endpoint, just like we did earlier. So I create some sample records. This is how a sample request body looks like with the feature names and the values. And I run calling the endpoint. There you go. I see the response, the prediction, and the model that is used. We can also send multiple requests where we get to see which models are being used at each response text, and also the prediction, whether the character is likely to be alive or dead. This is the end of A/B testing. In the previous lectures, we showed how to load data, train and register MLflow models into Unity Catalog. Last lecture, we used these models to create serving endpoint. In this lecture, we will combine all these steps together in a workflow. But first, let's cover some theory. When deploying Databricks jobs along with their dependencies, we have a few different options. The most common ones are Terraform, which gives you full infra as a code control, Databricks APIs, which allow for more custom scripting and programmatic deployment, and finally Databricks Asset Bundles, or DAB for short. Among these, Databricks Asset Bundles are the recommended approach. They offer a declarative YAML-based structure for defining jobs, libraries, and configurations in a single place. Under the hood, DAB already leverages Terraform, so you get the benefit of infra as a code without having to manage raw Terraform code yourself. This makes DAB a great balance between simplicity and power, especially for teams looking to standardize and automate job deployments in a scalable way. Databricks Asset Bundles, or DABs, are a way to package your code and configurations together in a structured and version control format. You define jobs, notebooks, models, and their dependencies using YAML files. This setup supports multiple environments like dev, staging, prod, and really fits into CI/CD pipelines. And Databricks workflows provide an execution or orchestration layer. Workflows let you run tasks like notebooks, scripts, or SQL queries on a schedule or in response to events. You can define task dependencies, set retriers, pass parameters between steps, and receive alerts if something fails. This is a typical workflow used in many ML pipelines. With Databricks bundles, you can package the logic, dependencies, and configuration files in one place, making your deployments cleaner and more reproducible. Let's start with Databricks components. Let's start with Databricks Asset Bundle components. Here is the basic structure of DAB configuration file. The first section defines the overall bundle configuration, the name of the bundle, which is required, Databricks CLI version, which specifies the CLI version being used, and you can also set the cluster by defining cluster ID. This overrides any cluster specification defined elsewhere in the bundle, and it only works in development mode, so it's not really recommended. Instead, it's better to define cluster configuration under the target section. Then we have the Git blog, which helps track where the code comes from, including the URL and the branch being deployed. And then we have the variables section, where we can define custom variables to reuse throughout our bundle. Each variable has a description and a default value. Other two important sections of DAB configurations are permissions and artifacts. The permission block defines access levels for all resources in the bundle, including jobs, experiments, models, and pipelines. You can assign different permission levels, view, manage, run, etc., to different entities, groups, users, service principals. This helps to ensure consistent access control is applied automatically when deploying the bundle. In this example, a group is granted view permissions, a user is granted manage permissions, and a service principal is allowed to run the resource. And then we have artifact section. The artifact section defines how your job dependencies are packaged and deployed. Each artifact gets a unique identifier, and the build defines the build process, and the files points to the source files. You can also specify where these files should go and what type they are. This is especially useful for packaging custom code, libraries, or configurations alongside with your job. And this section defines the include block, which is to bring any additional YAML configuration files into your main bundle. You can think of this as a way to modularize your setup, similar to imports in code. For example, you might have a separate YAML file that defines the job, another one for libraries, or even target specific overrides. By listing these files under include, they get merged into overall configuration at deployment time. This is especially useful when managing larger projects with multiple jobs or when sharing reusable components across bundles. Next week, we will see an example of additional workflow being added via this block. And the next section shows how we can define resources like dashboards, experiments, jobs, models, and pipelines within the bundle configurations. Each entry uses a programmatic identifier and maps to a corresponding REST API payload reference. While it is possible to define all types of resources here, we only recommend using this method for Delta Live tables and jobs. And it is because for other resource types like dashboards, models, or schemas, tracking changes and ensuring reproducibility becomes difficult when they are deployed through bundles. So to keep things traceable and maintainable, use this block only for jobs or DLT pipelines, which benefit from being tightly version controlled. In this part of the bundle config controls which files are synced to Databricks Workspace during deployment. By default, everything in your directory is synced, except anything listed in your .gitignore file. But you can customize this behavior using the sync block. Include explicitly includes files or folders, even if they would be ignored otherwise. And exclude explicitly exclude files or paths from being synced, especially useful for sensitive or irrelevant files. Paths define custom paths that should be synchronized, which gives you precise control over what is deployed. So use this when you want to avoid uploading things like large files or notebooks under development or any secrets. And this section defines targets, which are the different environments you can deploy to, typically something like dev acceptance prod. Only one target can be marked as default true, And each target can override any part of the bundle config like artifacts, clusters, variables, permissions, and more. Think of this as a scoped override layer. What you define under a target will take precedence over the base configuration. One key field is mode development. When this is set, it pauses all scheduled jobs, which is helpful to avoid accidental job execution during tests. Presets are commonly used to add name prefixes, set pipelines development mode, or pause all triggers, and limit the job concurrency or add metadata. And these are the important CLI commands that we will use. For this to work, you need to install Databricks CLI in your environment. Here is the example workflow we are going to create. The first task in the pipeline will be preprocessing. The second is train and evaluate model. If the model is better than the previous version, we will release a flag for model update and register the model. The last step is deploying the recently registered model by creating or updating an existing serving endpoint. As you can see, there are some parameters passing around. The orange ones are the parameters given as an input to my script. Blue ones are the outputs. These are explicitly defined in Databricks YAML file, which you will see in a moment. In the steps of the workflow I just showed, we are going to use the code scripts for different tasks that we already implemented in the previous lectures. Before going to the code base, let's remember the scripts we created in earlier lectures and how we will use them. In Lecture 2, we wrote Data Processor class and used the functions to process raw data into train and test. In ideal workflow setup, we would get new data periodically and merge that data together with our existing one to update our final train and test set. But in this example, we're not doing it. Instead, we are overwriting train and test tables in this step. In the next step, we are training and registering a custom model. We added an evaluation check after training. If the model is better, then we proceed with registration. And the last step is to create or update serving endpoint with the recent model that we registered. Now, let's go to our code base and see how these are implemented. In our code base, we have Databricks YAML file, which is our main bundle configuration file. Let's break it down and see what's happening in it. First, we declare the name of the bundle project. In our case, it's Marvel characters. Then we are modularizing our configuration by including a separate YAML file that defines the job resources. In our case, it will be a workflow and its tasks. In the next section, artifacts, we tell the bundle how to build the code that will run in the job. It will create a wheel file using UV-build, and it also passes the root path, which is where the build process starts. This artifact will be made available to the job when it is deployed. Then we define some global variables. And in the last section, we define the targets. We have 3 environments: dev, acceptance, and production. Each has a Databricks workspace URL, host, a profile, a root path for deploying artifacts and scripts, and some environment-specific variables. Now, let's deep dive into the job definition, which is the heart of this workflow. So we're going to look at model deployment.yaml in our resources folder. We are creating a job called Marvel Characters Workflow that is scheduled to run every Monday at 6 a.m. in European time zone. Whether it actually runs depends on the path to this variable. We are also tagging the job for traceability purposes. And here we define which wheel file to use. And below is the pipeline broken into steps. The first task we run is preprocessing. It executes process-data.py from scripts folder and it passes some arguments to the script. The next step is training model. It runs train register custom model.py from scripts folder, and it also passes some other parameters in addition to root path and environment. It passes git commit hash for traceability, the job run ID, which will be available during the run, and the branch name. The next step is a conditional task called model updated. It will check the output variable from the previous task which is train model, and checks whether it equals to 1 or not. If it is equal to 1, then it will proceed with the next task, which is deploying the model. So the last step is only executed if this conditional task is satisfied. In the last step, we execute deploy model.py, which simply creates or updates existing model endpoint with the latest version of the model. Now, let's go look at our scripts folder and see what we are actually executing. In scripts folder, the first script we run is preprocessing. This is a script where we load the Marvel characters dataset, process it, and then create train and test tables. This is what we have seen in lecture 2. We are already utilizing the same module that we created in lecture 2, data processor. We load the data, we create data processor instance, and we run preprocessing. And then we split process data into xtrain and xtest, and then we save it to the catalog as delta tables. In an ideal scenario, we would be getting new data periodically, and this data would be loaded into processor, and then it would be merged to existing train and test sets. But in our scenario, we don't have any data arriving weekly or monthly. Therefore, each time we execute this script, we load the same dataset and overwrite existing train and test tables in catalog. The second script we execute is train and register custom model. In this script, we initialize a basic model first, and then we load data, prepare features, train the model, and log the model, just like we did in lecture 4. Then we run another init function, model improved. This function compares existing latest model with the recent model trained and checks whether the model is improved or not. Let's go check what this function does. By using MLflow client, it gets the latest existing model version and it evaluates compared to the recent model trained. And it compares based on F1 score. If the recently trained model is performing better than the existing one, then it returns true. If not, then false. Going back to our main script, if model improved is true, then we proceed with registering a custom model. If you remember in lecture 4, the custom model was a special wrapper around the basic model, where we tweak the payload and change the logic. This is exactly what we are doing here, just like in lecture 4. We are creating a wrapper, passing the train model, and we're registering a new model, running log register model from Marvel model wrapper class. This will give us the latest version that is just registered under custom model. And this task is releasing two outputs. Model version, which is the version of the custom model registered just now, and the model updated flag. These two will be used in the next steps. If the model is updated, then we proceed with the last step, which is our deploy model script. In the last step, we are using the model serving module that we have seen in the previous lecture. What we're doing is we're getting the model version from task variables. And this is an example how you would get a task value from the previous steps. Train model is the name of the task that is executed in the previous step, and model version is the name of the variable that we want to get. This will tell us the model version that is just registered in the previous task. And we proceed with creating our model serving module by passing the model name and the endpoint name. And then we run deploy or update model serving function. This is the function that we have seen in the previous lecture. What it does is it first gets existing endpoints, checks whether the endpoint already exists. If not, it creates a new endpoint with the given name and the given configuration. And if it already exists, then it updates the configuration of the existing model serving endpoint. In our case, it will update the existing model serving endpoint with the recent model version. We have seen our bundle configuration and each script we execute in the workflow. Now, we will see how to deploy our bundle to our workspace. But first, Let's check if we're connected to our workspace. Everything looks green, so we are good to go. I will use the bundle CLI commands we have seen in the slides. For this to work, of course, you need to have Databricks CLI installed in your environment. The first command I will run is Databricks bundle validate. Oops. This will check our bundle configuration and confirms if it is correct. It says validation is okay, so we can proceed with bundle deployment. But first, let's go to our workspace and see what we have. In our workspace, we have Jobs and Pipelines section where we can see all the workflows. Currently, we don't have any. So let's deploy our bundle. This command will build all the dependencies and deploy our bundle. It will create a workflow in our workspace. Nice, deployment is complete. Let's go check our workspace. There you go. We just created our workflow. You can either run in the UI, or you can also trigger this workflow using Databricks bundle run. It will ask which resource to run. In this case, it's Marvel character workflow, and it will trigger our workflow. It's currently running, which we can also see in the UI. Once the job run is complete, the logs are printed directly in the terminal since we triggered the execution using bundle run. Here we see terminated success and all the outputs from different tasks. It's a lot of logs. Let's go check the UI. Here we see that the whole process is successfully completed. You also see the run details, the job run ID, start time and end time, total duration, the compute, which is serverless. And you can also go check the outputs from each task. All the logs are written in the output section of each task. In the previous lectures, we implemented machine learning pipelines step by step, including pre-processing, training, and deployment tasks. The last lecture, we combined all these together with Asset Bundle for workflow deployment. In this lecture, we will talk about catalog and workspaces, how data and assets are organized and accessed in structured way in Databricks environment. Then we'll go over a common Git branching strategy and then see example of CI/CD pipeline. We have already interacted with Unity Catalog. We used it to create delta tables and register models. For a workspace to use Unity Catalog, it must be attached to a Unity Catalog metastore, the top-level container for metadata of all data and AI assets. You can have one metastore per cloud region, and a workspace can only be attached to one metastore in the same cloud region. It is not uncommon for large organizations with international operations to have multiple Unity Catalog metastore. In Unity Catalog, assets are organized using a three-tier hierarchy within the same metastore. Catalogs, which contain schemas, and within those schemas, we would find various data and AI assets, such as tables, views, volumes, models, and functions. And they can be referred to using a three-part naming convention: catalog.schema.asset. In a typical setup, each team or machine learning project would have three workspaces: development, acceptance, production, or they would have three different catalogs with their own schemas. But there are a few important rules in this setup. All workspaces, development, acceptance, and prod, should have read access to production data. It is important to ensure consistency across environments. Each workspace can only write to its corresponding catalog. So dev would write to dev, acceptance to acceptance, and production to production. Importantly, users only have direct access to development workspace. This keeps things safe and contained during experimentation. When it comes to deploying anything to acceptance or prod, that can only happen through continuous deployment pipelines, so no manual pushing, which ensures security and traceability via service principals or managed identities. Let's also look at how this structure plays out with a typical data platform setup. Data engineering teams usually organize source data using medallion architecture, bronze, silver, and gold layers, each separated by environment. For example, they have bronze, acceptance silver, production gold, and so on. Each data product has its own schema, which helps with clear ownership and granular access control. Now, for machine learning teams, during development, they can read from the production or gold catalog. This means they can train models on high-quality, production-grade data from day one. That way, we avoid surprises caused by data inconsistencies and reduce model drift. When it comes to writing outputs like features or predictions, each machine learning workspace can only write to its own designated schema. So dev writes to MLOps dev, acceptance writes to MLOps acceptance, and so on. So how do we control who sees what and where they can access it? In Databricks, there are two types of securables, workspace level and Unity catalog level. Workspace securables are things like notebooks, clusters, and jobs. Access here is handled through ACLs, access control lists. Users can manage what they create, and admins can manage everything in the workspace. If you create Free Edition, you are the admin of your workspace, so you can manage everything. Unity Catalog covers things like tables, schemas, and AI assets. Access here is more centralized and defined at the metastore level with granular privileges. Metastore admins can transfer ownerships of objects, but every action is fully audit logged. We can also apply workspace bindings to prevent cross-project data access. For example, if a machine learning engineer is working on both hotel pricing and demand forecasting, you don't want them to accidentally access the wrong datasets. Unity Catalog supports open and isolated access modes. This allows us to strictly control which workspaces can access what. Finally, when organizing teams, we recommend giving full workspace access to only development environments. Use cluster policies to keep infra safe, and make sure users share what they create, because by default, only the creator has access to notebooks and jobs, and the endpoints. Without that, collaboration can hit a wall. Let's have a look at the example here. The hotel booking team has all privileges and managed permissions on the MLOps dev hotel booking schema. In other environments, they have only read access, which allows them to safely use production data for training and validation. SPNs have all privileges and managed access on schemas in the corresponding catalogs, and read-only access to Prod Gold hotel booking schema to ensure consistent data consumption across environments without risk of modifying production data. The privileges on the schema level are propagated to all underlying objects. Let's quickly remember Git flow. If you have used Git, you have probably come across Git flow, a branching strategy made famous by Vincent Driessen back in 2010. Short-living feature branches are created from main, like features foo, and developers can create pull requests to the main. This will trigger CI pipeline, and CI pipeline will run pre-commit checks, unit tests, and ensures version txt does not already have a use tag. At least 2 approvals are required to merge, so there is no allowed direct pushes to main. Once it's merged to main, then CD pipeline will be triggered. CD pipeline fetches the secrets dynamically per environment and deploys to acceptance and production. In an ideal setup, service principals are used for automation and CI/CD pipelines. Each environment has a dedicated SPN with scoped permissions limited to its corresponding workspace. This separation ensures that automation processes only operate within their intended boundaries, and follow the principle of least privilege. Now, let's go to our code base and see our CI/CD implementation. Let's start with the CI part. You will find our GitHub Action Workflows in the .github workflows folder. We are using GitHub as our version control, but keep in mind this setup might look slightly different on different platforms like GitLab, Bitbucket, or others. Let's open ci.yaml. We start with naming our workflow CI. Then we define when this workflow should run. In our case, it will run whenever someone opens or updates a pull request targeting the main branch. This way, we make sure all the checks and tests are executed successfully before merging code into production. Below, we define the steps. The first step is checking out the code from pull request using checkout action. This will clone the repo into GitHub Runner so that the next steps will have access to the code base. Next, we get the version from version.txt to see which tag would be released from this merge. Then we install UV, which is required for building our dependencies in the next step, and then we install all the dependencies. Then we run our pre-commit hooks for linting issues, formatting problems, or any custom rules defined in our pre-commit config.yaml. And finally, we run our test using PyTest. We have a test folder with some unit tests written for data processor class. So this step will execute those steps. This is a basic CI/YAML example. Let's now go look at the CD pipeline. We start by naming our workflow, CD. Then we define when this workflow should be executed. We have two cases, either manually, via workflow dispatch, or automatically, on every push to the main branch. This is a typical setup for CD pipelines when you want deployments to happen only when changes are merged to the main production branch. Then we create the job and the steps. We are using a metric strategy, which allows us to run the same job for different environments. Currently, it is configured for both acceptance and production. Then we grant write permission to this job, which is required to push tags later in the job. Then these are the environment secrets and variables needed for our authentication with Databricks. Secrets are pulled securely from GitHub's encrypted secret store. Then we proceed with the steps. We start by checking out the repository, just like we did in the CI. And then we install Databricks CLI to interact with Databricks Workspace programmatically. Then the next step configures the CLI authentication for Databricks. We use a custom profile named Marvelous. This is the profile used in Databricks bundle configuration, so Databricks CLI will expect to see the host and authentication method under this profile name. Then we install UV, which is required for building dependencies when we run Databricks bundle deploy. And then we come to the core of our CD process, deploying our bundle to Databricks. While we are deploying, we also inject the commit hash and the branch name via variables. These two variables are used in our bundle configuration. The last piece creates the tag based on the version in version.txt file. If we are deploying to production, then we read the version from txt, create a git tag, and then push this tag to a remote repository. This helps us mark the commit that we want to production, which is important for traceability and rollback. For our CD pipeline to run successfully, we need to make these environment secrets and variables available in our GitHub environment. So what we will do now, we will create a production environment in our GitHub repo. Then we will go to our Databricks workspace. We will create an SPN. Using this SPN, we will create client ID and client secret, and we will copy these secrets back to our GitHub environment. This is our main repository. In the settings, we have environments. We see two environments created so far, dev and acceptance. In each environment, we have two secrets and one environment variable, as expected by our CD pipeline. So we will create a new environment for production. We have the environment. So now we will go to our workspace and create an SPN for our client secret and client ID. In our workspace, As a workspace admin, in the settings section, you will see Identity and Access Management. Here you can manage all the access and permissions. We go to Service Principals, and we see the SPNs created so far. We already have SPN for dev and acceptance. Now we will create one for production. We will add new, we will give it a name, production SPN. Now we created production SPN. Using this SPN, we will create a new secret by clicking Generate Secret. We will give it a lifetime, and then it will give us the client ID and the secret. What we need to do is copying these variables back to our GitHub environment. So I go to my production environment, and I add them as first client ID. Let me check whether if I copied the right one. Okay, copy the client ID and add the secrets. Now I will add the secrets. Add another one. Okay. Now I also need to add Databricks host as environment variable. I can simply copy this from my URI. All right. Now we created the environment and the variables and secrets expected by our CD pipeline. Now, what we will do is creating a pull request to trigger CI pipeline and then merging that pull request to trigger CD pipeline. I already have a feature branch called basically demo. I will create a pull request from this branch now. It is only updating the README file, so it's a very lightweight pull request. When we create, it will trigger the CI pipeline, and we will wait for it to be successfully completed. This is the CI that we've just covered. So it runs every step we've just seen in the ci.yaml file. Getting version control, installing UV and dependencies, running pre-commit checks, and all the tests as a last step. All right, this pipeline is successfully completed, so I can go back to my pull request and then merge. Ideally, we would expect someone else to approve this merge request, but for demo purposes, I will merge my own pull request without getting any approval. The moment I merge, it will trigger the CD pipeline, which you can see in the Actions section. This is the pull request trigger that I just merged. It is running for both acceptance and production environment, and for each run, it fetches secrets and variables per environment. Acceptance is completed. Production is also. Now what we expect to see is each environment run created a new workflow in our workspace. Let's go back to our workspace and see what we have. Jobs and pipelines. Yes, we can see two new workflows being created. Acceptance Marvel character workflow is created using acceptance SPN, and Marvel character workflow is created using production SPN. Each workflow is reading and writing to its corresponding catalog. We have catalog for dev, acceptance, and production. For these workflows to run successfully with the given identities, meaning SPNs, we need to give access to those SPNs for their corresponding catalogs. In catalogs, we have acceptance, dev, and prod. For acceptance catalog, in the permission section, we need to grant our acceptance SPN to be able to read and write to this catalog. So we search for our SPN, acceptance, and we give all privileges to this SPN. We need to do the same for our production catalog. Permissions, grant, and search for production SPN. And we give all privileges. Now we are able to execute these workflows. In this lecture, we have seen example workspace setup with different catalogs and environments, creation of SPNs, and example CI/CD pipelines. Next lecture, we will talk about monitoring. See you there! So far, we walked through the key components of classical machine learning pipeline, starting with the pre-processing, followed by training, and finally model deployment using delta tables and MLflow. In the previous lectures, we also learned how to deploy workflows using data asset bundles, which help package the code and configuration in a structured way. In the last lecture, we covered CI/CD pipelines, including how to automate deployments and manage environments, along with authentication using service principals for secure and production-grade access. Now we have come to the last piece, monitoring. Let's start with talking about what things to monitor in ML system. First, the generic monitoring. These are the standard checks you would have in any production system. System health. Are all services up and running? Are there any signs of CPU or memory pressure? Errors. Are we seeing spikes and exceptions, failed API calls or timeouts? And latency. How quickly is the system responding? For real-time systems, even small increases in latency can degrade user experience or downstream processing. And then we have ML-specific monitoring. This is where things get a bit more nuanced. First, we have data quality checks. Are we receiving data in the format we expect? Are there missing values, unexpected ranges, or broken pipelines? Data drift, which refers to the changes in the distribution of incoming data over time. While it's often discussed, it's also a bit questionable. Not every drift is harmful, so we need to ask, is this drift meaningful or is this just a noise? And then there is model drift. Unlike data drift, this is about the performance of the model itself degrading over time. Maybe it no longer predicts accurately due to the underlying changes in real world. And then we have cost and business value related metrics. Even if your system is technically working, it is important to ask, is it worth it? Are we optimizing our resources usage? Are we paying for GPUs for 24/7 for a model that only runs once a day? Are we moving the needle on key outcomes? Higher conversion, lower churn, faster fraud detection, whatever your goal is. And KPIs. These vary depending on the use case, but they are ultimate performance signals. And finally, we have fairness and bias-related metrics, especially important in sensitive use cases like fraud detection or loan approvals. You may need to monitor and mitigate biased behavior to ensure compliance and ethical usage. In traditional software systems, if you keep everything the same, the code, the model, environment, infrastructure, you can expect exactly the same behavior every time. It is predictable and deterministic. But in machine learning systems, it's different. Even if all those components remain unchanged, your model's performance can degrade and behave differently. Why? Because ML systems are heavily influenced by statistical properties of data flowing through them. So if the user behavior shifts, or there are seasonality changes, or if upstream data pipelines start emitting slightly different distributions, your model might start underperforming. This is why MLOps introduces new challenges that don't exist in traditional DevOps. We are not just monitoring the system components, we are also monitoring data drift, model drift, and the health of statistical assumptions. Let's remember data drift. Data drift happens when the distribution of the input data shifts over time, even if the relationship between inputs and outputs stays the same. Take the housing price prediction example. Suppose a lot of new houses enter the market in a certain district. People's preferences haven't changed, and the relationship between features and the price remains stable. But because the model hasn't seen enough examples of new houses, its performance drops. Not because the logic changed, but because the data shifted. So in this case, data drift is the root cause of decline in accuracy. And it might also signal model drift, which means the model no longer generalizes well to the current data. Let's move on to model drift, which is also known as concept drift. It occurs when the relationship between input features and the target variable changes over time. In other words, the model's original assumptions about how inputs relate to the outputs no longer hold. Let's go back to our housing prices example. Suppose new houses enter the market and the government introduces a subsidy for families with children. As a result, larger houses start selling for lower prices. This is a shift in the underlying relationship between features like house size and the final price. Even if the input data distribution doesn't change much, the model's predictions will become less accurate because the rules it learned no longer reflects the reality. Here's a great example that shows why we shouldn't panic just because data drift is detected. Let's look at the left-hand side first, the temperature distribution over time. The blue violins represent the reference period, when we trained or tested the model. The red violins shows the periods where data drift was detected using statistical method, in this case Jensen-Shannon distance. So yes, statistically speaking, the distribution of the input feature temperature has shifted significantly. But does that mean the model is failing? Now look at the right-hand side. This is the model's realized performance, measured using mean absolute error. The vertical gray line separates the test and production periods. The red dashed line is performance degradation threshold. Even though the model sees drift in its inputs, the blue line representing mean absolute error never crosses the threshold. So the model is still performing well, even under changed data distribution. So takeaway? Not all data drift is harmful. Sometimes drift is just noise, or the model is robust enough to handle it. That is why in MLOps it's important to track both data and performance before taking action. This example is taken from a nice article from NaniML. I highly recommend you to check it out. Now, we're moving on to lakehouse monitoring. Databricks offers lakehouse monitoring, which is a powerful tool that helps you track the quality and statistical properties of your data and monitor the performance of machine learning models, all from within Databricks ecosystem. Depending on the scenario type, whether it's inference, time series, or snapshot-based, Databricks automatically generates a few key components to help you track model and data health. Profile metrics table, which captures basic statistics like averages, null rates, cardinality across your features. Drift metrics table, which calculates how much the current data deviates from the expected or reference distribution. And the pre-built dashboard so you can visualize all this in real time without having to create complex queries from scratch. Now for inference and time series scenarios, which are both time-aware, Databricks slices the data into monitoring windows. You can pick options from like 5 minutes, 30 minutes, 1 hour, 1 day, or even 1 year. This gives you the flexibility to detect both short-term anomalies and long-term drifts, whether you are monitoring a high-frequency model in production or a slower-moving business process. The purpose of Profile Metrics table is to store summary statistics for each column in each time window, including slices or groupings. You would find some computed statistics like count, null, distinct count, mean, frequent items. And for inference log, it also includes accuracy, confusion metrics, precision, recall, etc. And the purpose of drift metrics table is to track how columns distributions change over time using drift detection techniques. There are two types of drift: consecutive, which compares the current window to the previous one, and a baseline, which compares the current data to a reference baseline table. And you would see some computed drift metrics, statistical test, distant metrics, and deltas. Here is a nice table that lists the methods and different data types. Some methods work for both continuous and categorical data, like Jensen, Shannon, and Hellinger. And some methods work for only continuous features, like Wasserstein and Kolmogorov-Smirnov. And chi-square and L-finity are only suited for categorical data. For detailed information of each metric, you can check out these links. We're moving on to inference tables. Inference tables are a built-in feature to log model input and prediction from a serving endpoint directly into a Delta table in Unity Catalog. This provides a simple way to monitor, debug, and optimize these models in production. Once enabled, they automatically capture request and response payloads, as well as metadata like response time and status codes. Enabling them is very easy. You would need to check Enable Inference Table box when editing a serving endpoint. We did this in Lecture 6. But remember, the workspace must have Unity Catalog enabled, and you would need the right permissions to create and manage the associated Delta table. It's important to note that inference tables alone cannot be used directly for monitoring. They simply log raw inputs and predictions from the serving endpoint. To enable actual monitoring, such as tracking drift or performance, you need to process this data into a structured format known as inference profile table. An inference profile table would typically include a timestamp for when the request was made, the input features, the model's prediction, and optionally the ground truth label for comparison. Once this table is created, you can use tools like Lakehouse monitoring to generate dashboards, track model quality metrics, and detect issues over time. Ideally, you should set up an automated job that processes the raw inference table into a structured monitoring table. This monitoring table would be used to update or generate a metrics table and automatically update the dashboard. You can also configure alerts, so you are notified when performance drops or data shifts, helping you take quick actions like retraining or redeploying the model. And this is an example for real-time inference. Here, the model is retrained weekly, and the updated model is deployed to the serving endpoint. Separately, when ground truth labels arrive, a workflow updates the monitoring table used by Lakehouse monitoring. These are two distinct workflows, one for training and deployment, another one for monitoring, each running on a different schedule. This separation allows for modularity and scalability, especially in production environments. Now, we are going to see our example code for creating monitoring table based on inference logs. This lecture, we are going through Lecture 10, Marvel Create Monitoring Table notebook in Notebooks folder. And also, we are introducing a new module in our source code called monitoring.py. Let's quickly go through what monitoring.py has. We define an helper function for creating or refreshing monitoring table. This function simply processes the inference data from Delta table, parses the request and response JSON files, and writes the resulting data frame into a Delta table for monitoring purposes. We start with reading the raw inference logs, which include JSON-encoded request and response data from Delta table. And then in the next section, we parse and unpack the input features and model predictions. You may recognize these column names from our payload structure. Then we proceed with cleaning and validating the data, filtering out any rows with null or invalid predictions. We may also need to change some data types for monitoring table. And at the last step, we write our inference table, parse inference table as model monitoring to our catalog. And then we check whether the Lakehouse monitoring is already enabled for this table. If it is, then we refresh the table. If it is not, we proceed with creating monitoring table, which is the function defined below. This function creates a new monitoring table for our model monitoring. Here we define some configurations. We set the problem type which is classification, we pass the prediction column name, the timestamp column, and we define granularity, which means the metrics will be aggregated and refreshed in 30-minute time window. This SDK function will quickly create a dashboard where you can see your monitoring results. In an ideal setup, just like we have mentioned in the previous lecture, we would have a separate workflow which updates our monitoring table and the dashboard. For this one, we introduce a new script, which is refreshmonitor.py, which simply runs the same code as we've seen in the notebook, create or refresh monitor. And for this script, we create a separate workflow in our bundle. In the resource section, you will see bundle monitoring.yaml. If you remember from the last lecture, we have modularized our bundle deployment. So we have Databricks YAML file, which is our main bundle configuration. And here we include our monitoring workflow. You can either do this or simply add a star to include all the resources available in the resources folder. Once we do this, we can now Once we update our main bundle configuration with a new resource, we can run Databricks bundle validation and deploy to. Okay. Once we update our main bundle configuration with a new resource, we can run validation and deploy our resources to create a new workflow for monitoring piece. Bundle monitoring has only one job, one workflow, and one step that runs refresh monitor script from scripts folder. Let's check if we are connected to workspace. We are connected to our workspace. Everything looks green. So let's run some CLI commands that we have learned in the previous lecture. I will first run Databricks bundle validate to validate my configuration. Looks okay. So I proceed with Databricks bundle deploy. This will deploy all the resources defined in my main bundle. In this case, it will deploy or update existing model deployment workflow and create a new workflow for monitoring piece. It says it's complete. Let's go to our workspace and see our pipelines. Yes, here we see a new workflow being created for monitoring script, and it has one task to execute refreshmonitor.py.
Thank you for following our course. We hope you learned something insightful and valuable along the way.
It's been a pleasure having you with us. If you are eager to go deeper, check out our mailing course. We offer extended content, weekly assignments, direct feedback, and hands-on experience. It is the perfect way to get your hands dirty and level up your skills.
We are also launching MLOps with Databricks course later this year. We have limited amount of spots for the first cohort, so be there early and secure your seat.
Don't forget to follow us on social media. The details and the discount for the next cohorts are in the description. See you around!